Uh, thank you, Xinan, for accepting our invitation. Today we have a journal club from Xinan Zhou from Kavli Institute for Theoretical Sciences, the University of Chinese Academy of Sciences, with the topic Power Corrections to EEC from Large Spin Perturbation. Thank you, Xinan. Take it away.
Okay, thanks a lot for the invitation, and yeah, very happy to be virtually here and present a recent work with my colleagues in Zhejiang University. Both of them are experts in QCD, and well, introduced me to this very interesting topic of energy correlator. Yeah, let me also mention here that the junior collaborator here, Hao Chen, is also on the job market this year, and he's super good. So today's talk is about how to use some techniques, well, standard techniques from the analytical form bootstrap, and to compute something that's of interest to QCD people. So let me start by defining what this energy correlation is. So basically, it is just some cross section with some weight, and it measures the differential angular distribution of some particle scattering experiment. So let's think, for example, when where you have E plus and E minus, and you apply them against each other, and then you create some virtual state V. For example, let's imagine it is some like virtual photon, and the virtual photon decays into a bunch of stuff, and among this decay product, we are going to measure these particles with two detectors, detector 1 and detector 2, as in this figure here. And these two detectors, they measure respectively particle A and B. These two particles A and B, they go into detector 1 and 2 respectively. And there's also a bunch of other particles which are not measured, and they're encoded in this everything here. So this EEC is basically just this differential cross-section weighted by this factor EA times EB divided by Q squared. Here, EA and EB are the energies of the particles detected by detector 1 and 2 respectively. And this Q here is the total center of mass energy of E plus and E minus. And there's this EEC defined as such also depends on a parameter chi here, where this chi is just the angle between these two detectors. And because you can always put it on a plane, so this chi goes from 0 to pi. And this EEC is infrared finite, which makes it good observable. Now in QCD, at high energies, the outcome of this E plus E minus scattering is dominated by events with two jets. And therefore, if you look at this EEC, you find that the dominant contribution comes from two limits. The first limit is a collinear limit where chi goes to 0, which means both detectors are measuring the same jet. And then there's also another limit, which in which the two detectors are measuring two jets in two different directions. So this is the limit where chi goes to pi, and it's called the back-to-back limit. And this dominant contribution in these endpoint regions is manifested in the perturbation theory as large logarithmic corrections. Now, this definition here is very physical and intuitive to understand, but in practical calculations, it's a bit cumbersome because if we want to compute this EEC from amplitudes, we need to sum over basically all the final states, which is quite complicated, and also in the calculation, there are intricate cancellations of infrared and collinear divergences. There is actually another definition, which is more convenient, and it is definition in terms of correlation functions. So in this definition, we basically need to consider a 4-point function. So it involves these current operators J, and also some other operator E, which is the energy flow operator, which I'm going to talk about in a sec. So this current operator, you have two of them. So one is like a source, and the other one is a sink. So basically, just creates the final states of this E plus E minus scattering. And this curly E operator, the energy flow operator, is the detector in this experiment. And it was first defined in this paper by Hoffman and Malastena. And basically, what does this to measure the energy flux per unit solid angle in some direction on the celestial sphere. So more precisely, it is defined from the stressed angle tensor, and we saturate the indices with some dimensional polarization vector. This polarization vector is null. So the first component we can set to 1, and then you have another 3-dimensional vector which specifies the direction on the celestial sphere. And you further need to integrate this operator along a null direction. And this operator is also moved to the infinity. So you can also think of this operator like in terms of this picture. So basically, you just put some detector first at some finite distance, and you integrate over it over time, and then you move this operator to infinity so that it becomes null. One comment I want to make about this EEC, which is quite clear from this definition, is that it is defined on a Weizmann 4-point function in the sense that it is not time ordered. And therefore, the information captured by the EEC is intrinsically Lorentzian. Before I go on, are there any questions? No? Okay. So in this paper, actually, we are not really going to attack QCD, which is, of course, probably more interesting. Instead, we are going to deal with a toy model of that, namely the 4D n equals 4 superior Mills theory. The reason we want to do that is actually threefold. So, of course, QCD is very difficult. So we want, in order to make more progress, we want to more analytical progress, we want to use more symmetry, which, well, I mean, these symmetries are not there, but it will simplify the calculation by quite a bit. For the n equals 4 superior Mills, it has not only conformal symmetry, but also supersymmetry. And we'll see that allows us to get a lot of mileage in this calculation. Now, studying for the n equals 4 superior Mills is also has some connection with the model which we really care about. So it turns out that in many explicit examples, that the energy correlator in QCD and in n equals 4 superior Mills, they share a lot of structural similarities. More precisely, you find that you have the same type of polylogarithmic functions appearing in both theories. So one use of this fact would be, you can try to compute these objects in this more simplified theory of n equals 4 superior Mills, and then you can now you have a basis of functions which you can use in QCD and try to bootstrap the EEC there. And also there is the conjecture by Belitsky and collaborators where they conjectured that this EEC in the back-to-back region where chi goes to pi, what we compute for the n equals 4 superior Mills describes the maximal transcendental part in QCD. So these are the motivations why we are considering EEC in 4D n equals 4 supermills. Now, in this definition, where we have some currents in n equals 4 supermills, the appropriate choice would be the asymmetry current. And following this definition, if we want to compute EEC, we should start from the correlator of JTTJ, the spinning 4-point function. However, in 4D n equals 4 supermills, both the asymmetry current and the stress tensor current, they live in the same multiplet, namely the stress tensor multiplet. And because we have superconformal symmetry, it actually is sufficient to only look at the 4-point function of the superprimary of this stress tensor multiplet. So these are the superconformal primary are the so-called 2D prime operators. And it just trace xi and xj, and you take the symmetric traceless interpretation. And here this xi is just the six scalars in 4D n equals 4 supermills. And similar to this energy flow operator here, we can also define some scalar detectors in terms of this 2D prime operator. And will be more precise, but the upshot is that you will see that the scalar EEC, where you measure the scattering out using scalar detectors, is actually proportional to the real EEC, which is defined in terms of the stress tensor. Okay, so yeah, so let me just briefly recap. So here, because of superconformal symmetry, the problem is very much simplified, and we only need to look at the 4-point function of 4 of these 2D primes. Now, let me briefly remind you here what is the superconformal kinematics of such 4-point function of this 2D prime operator. So it has been known for a very long time that there is, because of superconformal symmetry, the function satisfies the so-called partial non-renormalization theorem. So what that means is basically you can split this 4-point function into 2 parts, where you have this correlator in the free theory limit, where g is equal to 0. And then you also have another part which corresponds to quantum correction. This quantum correction part is multiplied by a factor r here, which is completely determined by superconformal symmetry. And then there's another function phi here, which is called the reduced correlator. Yeah, I should also mention here, when I write O xi yi, what I mean is you need to saturate the asymmetry indices by some 6-dimensional null vector, so that we don't need to carry around these indices. And this y here, so y is null, so yi times yi is 0. And also here I introduce this shorthand notation, yij squared is just yi times yj. And because of this factor here, it already carries all the asymmetry weights. So the reduced correlator here does not depend on asymmetry. It only depends on the conformal cross ratios U and V. And this reduced correlator, you can really view it as a correlator, and it has a crossing symmetry. In particular, it obeys this crossing symmetry, where if you interchange U and V, it is invariant. Now, to define this scalar EEC, where the detector is made of scalar of the 2D prime, we need to choose some appropriate polarization. It's a bit technical, so I'm not going to give you the details of how to choose these polarizations, but the upshot is that we are basically just projecting in the S channel, which is projecting the asymmetry representation to the so-called 105 representation. So yeah, so essentially you have 2D prime times 2D prime, you get a bunch of asymmetry representations, but here the presentation is such that you have only just 105. And with this choice of the position, you find the right-hand side becomes the first line, and we can further collect these terms and write it into two parts. So there is the part which comes from which is independent coupling. It receives contributions from the short multiplets, and then there's another part which comes from the long multiplets, which depends on the coupling. And at one loop and higher, this function f here is just this function 5 multiplied by some powers of u and v. So what essentially phi and f here, they're equivalent. Okay, so this is just a very standard stuff about the 2D prime 4-point function in n equals 4 polynomials. Now, starting from this 4-point function, we can define this EEC by first doing two light transforms to define these detectors, scalar detectors. So basically, it's the same as this energy flow operator, where we, but here we don't have any Lorentz indices, so we just integrated it along another direction, and then we send this particle to infinity. And after doing that for two of the particles, 12 operators, we do a Fourier transformation for the source and sink, so that it have a definite momentum q. And then we define this scalar EEC, and it's proven in this paper by Bielitsky and others that it is proportional to the real EEC defined from the 4-point function JTTJ. It is just up to a factor which depends on this momentum and the polarizations. Now, I also want to mention that for n equals 4 supermills, this EEC has a very simple, particularly simple representation in melting space. So the reduced correlator, we can, it's a function of u and v. We can melting transform it, and with the dual variables on u and v becomes j1 and j2, and we define this melting amplitude m of j1 and j2. Now, in terms of this melting amplitude, the energy correlator can also be written as a two-dimensional inverse melting transformation, where you also have this melting amplitude of this reduced correlator, and it's multiplied by some kernel k, which depends on j1 and j2, and also this variable y. And this variable y is related to this angle in this way. So for example, yeah, so in the small angle limit, y goes to 1, and in the back-to-back limit, y goes to 0. So in principle, if you know the melting amplitude, you can just plug into this formula, and you can work out what this EEC is. Now, let me quickly mention what has been known about EEC in n equals 4 supermills. So it has been studied by many authors, and at weak coupling, it is known to 3 loops. People also know this EEC to higher loops, actually to orders in the coupling constant, but only to the leading order in the collinear limits and the back-to-back limits. So as I said earlier, so in principle, if you know the correlator of the prime operator, then essentially you just need to do two light transforms for two of the operators, and then do another Fourier transformation. Then you can get the EEC. Alternatively, if you know the amplitude, the Mailing amplitude, you can also perform the integral and obtain the EEC. But in practice, however, this is extremely difficult, and people only manage to do that to 3 loops. And in this talk, I'll make some improvements. Well, not for the full EEC as a function of the angle, but mostly, but only in this back-to-back limit. And this improvement is possible by using some standard tools in the analytical form bootstrap. And I'm going to show you how to compute this EEC in this back-to-back limit to the next 2 leading orders in the logarithmic corrections, and also to the next 2 leading order in power corrections. And the result is valid to all orders in the coupling. Sorry? This is not for QCD. This is for n equals polynomials. Yes.
Yeah, right. Down in QCD.
Sorry, I cannot hear you very clearly. The question is, what is known for QCD? Yeah, I'm not. Yeah, I don't know off the top of my head. I think it's probably less. I mean, the people. Yeah, the computation is different. Yeah. So here we have like the shortcut. Yeah, we have this shortcut from this correlator to EEC via this Mailing transformation, but that is not there for QCD.
Oh, okay.
Yeah. I mean, there's also a lot of results, but yeah, yeah. But yeah, off the top of my head, I'm not sure what the precise statement is. Yeah. Right. So now let me tell you how to do that. But before that, before I state the strategy, let's first go back to this Mailing representation I was just mentioning. So yeah, so let's look at the Mailing representation of both EEC and the reduced correlator. It is quite clear that, well, first of all, the back-to-back limit of this EEC, where y goes to 0, it is related to the double light cone limit of the 4-point function, where both u and v goes to 0. So essentially, in the small y limit, we want to close the contour of J1 and J2 to the right, and we pick up the poles on the real axis, the right half of the real axis. And this is also the same thing like in for this reduced correlator. Right, actually, this was already pointed out in a paper by Kochemsky. And furthermore, actually, comparing these 2 definitions, these 2 Mailing representations, you can suggest that we should identify this u to the J1 and the v to the J2 factor with this kernel k, well, divided by some factor of y. And we further take derivatives of this this map with respect to J1 and J2, and then we get powers of log u and log v. So if you do that explicitly, you find the following map between the logarithmic singularities in this 4-point function,
and the logarithmic singularities of this EEC in the small y limit. So this is the explicit map. Okay, now with this in hand, I can tell you what is our strategy to compute this EEC in the back-to-back limit to the subleading orders. So the first step to do that is we first compute this reduced correlator in the small u limit. And we want to compute it to the next leading order in the logs, and also next leading power in V. So at nth loop, we would expect at most log u. This is because like these logs are associated with enormous dimensions, right? So we can have the tree level enormous dimension to the nth power, and that corresponds to log u. Yeah, so here I'm doing things a bit more schematically. I still know these coefficients as A, and B, but later I will be more precise of their interpretation in terms of OP coefficients and the enormous dimensions. So we have log u to the nth power, and by crossing symmetry, we should also have log v to the nth powers. Therefore, we have such a term. So this is like the leading logarithmic singularity. And in subleading means that we can have another power less. So we can have log u times log v to the n-1 power, and also the other way around. Now, subleading in V means that we can have a subleading power in V, which means that we can also have power correction to this. So V will also go to 0, so we can have something that's linear in V. That in this expression, the only data that is involved is the operator with the lowest twist, namely twist 2. So these are like the Konishi operator. And also we only need the tree level and the one loop data of this twist 2 operators. So this is because, like, for example, in this log u to the nth power, you should have, the free theory OP coefficient times tree level gamma to the nth power. But here you can also have log u to the n-1. So in particular, it can be, this tree level gamma to the n-1 power times the one loop correction to the OP coefficient. But beyond that, we don't need anything. We just need the twist 2 operators at tree level and the one loop. And such data has been obtained a long time ago in the literature. So this is step 1. We want to compute this correlator in small u and small v to this order. The next step is to use the crossing symmetry. So I told you earlier that under UV interchange, this function phi is invariant. So that allows us to get from step 1 some additional terms. So these additional terms, I underline them with this red line. And this leading power, subleading power in V now translates to a power of U. Now note these terms are proportional to U. They correspond to operators with higher twist. They are twist 4 operators. And this operator, the data of such operators is actually quite difficult to extract because at twist 4 there is operator mixing. But thanks to crossing symmetry here, we just obtain them for free, and we do not need to import them. Now the final step is to exploit the I showed you earlier. where you map these logarithmic corrections to the 4-point function, and you map them to logarithmic corrections to the EEC in the small y limit. And in the end, what we are going to compute is the leading log terms in y, and also subleading term in the logs, and also power corrections. So in this strategy, in this three-step strategy, the most non-trivial part is the first step, namely we want to compute these logarithmic corrections, and but this can be easily handled by using the large spin perturbation theory. Is there any question about the strategy or what we want to compute?
So let's go a bit further in your corrections, right? Because there's more data available in the literature. So
Sorry.
You're saying that the level of loop is known, but actually there's more results are known, right?
Sorry, could you say a bit louder? It's a bit.
So the question was, you're saying that you know the data for tree level in one loop, but actually there's
Data for 2 and 3 loops.
There's data for 2 and 3 loops.
In principle, you
Yes.
could go a bit further in your analysis.
So in principle you could go a bit further, right?
But if our goal is just to compute EEC like to this order, like we only need a tree and one loop. Yeah. Yeah. So that's the goal, and this is the data we need. Yeah. But you're absolutely right. Like in the literature, we definitely have more data. Yeah.
Yeah. Okay. Thanks.
Thanks.
Thanks for the question. Okay, so now let me just very briefly review the idea of the large spin perturbation theory and how we are going to use it in our calculation. So let's start from very basic stuff. So we know that in 4 dimensions, the conformal block takes the following form. And if you go to the small limit, which corresponds to, z bar goes to 1, this conformal block can have at most a log v divergence. This is because, like these two F1s have a branch point at z bar equals to 1. However, as I was describing the strategy, we saw that the reduced correlator are expected to have higher powers of these logarithmic of these logs. So these are usually called enhanced singularities in the literature, and clearly this is not possible by using finitely many conformal blocks, and this only comes after we sum over an infinite number of conformal blocks. And the large spin perturbation theory is the ideal tool to systematically deal with these infinite many conformal blocks and also these enhanced singularities. And this method is based on some objects called the twist conformal blocks. So the idea of these twist conformal blocks is the follows. So in the free theory, if you do a conformal block decomposition, you find that these operators appearing, they have degenerate conformal twists. So the conformal block decomposition, you can write it as a sum over conformal twists. So you, in doing so, you have already summed over the spins, and you define some object h of a certain twist, which is called a twist conformal block. So basically, you just take the free theory of B coefficients and you sum over the conformal, and you sum and then you have a sum of conformal blocks over the spin L. And here, actually, I have already adapted this story to n equals 4 super Mills by defining this boldface G. So this boldface G is related to the bosonic conformal block by a shift of 4 in the conformal twist. And the shift comes from superconformal symmetry. So in terms of the reduced correlator, we only need to do a bosonic conformal block decomposition, and that corresponds to the superconformal block decomposition for the full correlator. Okay, so that's the free limit. But when we turn on the interaction, the degeneracies in the conformal twist are going to be lifted. And we need to compute corrections, which have the following form. So this we need to insert some function of L, this kappa, and this kappa can be expanded with respect to large spins in the following way. So here, the expansion is most natural in terms of some object called the conformal spin, this capital J here, and it's defined as follows. And this expansion contains only negative even powers of the conformal spin, and as well as some powers of log of this conformal spin. And because of this form of the correction, we need to generalize our definition of the twist conformal blocks by inserting these powers of J and also log J squared into this definition of twist conformal block. And as a result, this generalized twist conformal block carries two indices, M and I, which measures how many powers of 1 over J squared you have, and also how many powers of log J squared you have. And you can view these labels as how far away you are from the free limit. Okay, so this is just definition. Now we need to think about how we can compute these twist conformal blocks. Now, the computation of these twist conformal blocks is in general very difficult, if not impossible. But in the limit where V is very small, and if we only care about the enhanced singularities, then it becomes tractable. So in this limit, it follows from the form of the conformal blocks that the twist conformal blocks themselves also become factorized. So you find, sorry, this question?
No, it was outside.
Okay, yeah. So basically, you just use this expression here. You take the z bar goes to one limit. You find, and you drop all the other non-enhanced terms. You find the conformal blocks are factorized, and as a result, the twist conformal blocks, they are also factorized. And from this h here, we define another function h bar, which only depends on z bar. And this z dependence just becomes this 2f1 here. Now, on the other hand, we know that the conformal blocks, they are eigenfunctions of this Casimir equation. So here I have modified this Casimir operator slightly by adding a constant shift, such that the eigen value of this this shifted Casimir operator acting on this G gives you just the square of the conformal spin. And using this in the definition, here you can find this J squared allows you to move between different twist conformal blocks. So basically, if you act on the twist conformal block with the Casimir, you decrease the value of M by 1. And this going to the small v limit translates also to a recursion relation for this h bar function, where this differential operator d bar here is reduced from this conformal Casimir, and it is a differential operator acting on the z bar coordinate only. Okay. Now, what we are going to do is to just use this recursion relation and compute these differential, compute these two conformal blocks. And this method actually already appeared in this paper by Henriksen and Lukowski from 2017. So, and the method can be, again, outlined in a few steps. So the starting point of our calculation would be the case where both m and I equal to 0. So in this case, also if we choose 2, you can actually just explicitly resum the conformal blocks, and in the limit, z bar goes to 1. Also, well, for convenience, let me also define this epsilon, which is 1 over z bar. Then the v goes to 0 limit is also the epsilon goes to 0 limit, and you find that it has the following form. Now, to get the two conformal blocks we need to do the following. So we need to act on this this starting point repeatedly with this d bar operator. So the d bar operator is going to give you is going to decrease the value of m, and so that, you know, for these negative integer values of m, and you can always reach them by acting with this d bar. And then after doing it a couple of times, you can get a general formula for all these negative integers. And it looks as follows in the small epsilon limit. And once you have this formula for negative m, you can analytically continue it to positive m, actually to all values of m. Now, the third step is to, after you have this this formula for general m, you can now take derivative with respect to m. So from the definition, if I take derivative with respect to m, I'm going to get powers of log j squared, and that is how we can go in this direction of I away from I equals to 0. So again, like you can do this for m equals to around m equals to 0 and m equals to 1, and for arbitrary I and small epsilon, you find the following expression. And in fact, for our calculation, only m equals to 0 and m equals to 1 is needed, because if we expand the reduced correlator to this order I just mentioned, you find that the singularities can be matched by just m equals to 1 and m equals to 0 to conformal blocks. This expansion actually also, well, you also have these higher m's, but for our purposes, we do not need the information of these higher twist conformal blocks with bigger m. You can attempt this by just repeatedly acting on both sides with this d bar operator, and then you keep comparing the singularities, you can get these coefficients for these higher m twist conformal blocks, but we will not need them. So let me just summarize what we did here. So basically, we just start from a case where we explicitly know the twist conformal block. We use the recursion relation to first go to get an analytic expression for arbitrary m. Then we take derivatives. Then we get the logs. And then we compute these twist conformal blocks, which are needed for our calculation. Okay, so now after we have computed twist conformal blocks, we are ready to implement the strategy I outlined. So first we need to do is to compute this reduced correlator in the small u limit. And in the small u limit, the conformal block decomposition takes the following form. So here here we are now more explicit about these numbers, capital A and capital B, in the description of the strategy. And they are expressed in terms of the tree level and the one loop level data for the twist2 operators. And actually, for our calculation, we do not even need to use the exact form of these tree level and one loop data. All we need is the large spin expansion of these data. And we only need them to the order of 1/j². So here, if you look carefully, you also find there are these autopowers in the conformal spin. However, if you plug everything into this expansion, and you find that all the odd powers, they cancel out, and you get only negative even powers, and you can rewrite the result in terms of the twist conformal blocks according to their definition. Okay, now these twist conformal blocks, as I showed you earlier, we have already computed. So let's just plug this into here, and you find the following explicit form of this reduced correlator in terms of these logarithmic corrections. Now, so this is for this f. So let me remind you, there's a minor difference between this f of n and phi of n just by some powers of u and v. So you can translate this back to this phi again, and then use crossing symmetry between u and v to complete it to the subleading next to leading in log and next to leading in powers. And here you have these powers proportional to u, which has encodes the twist4 data, but they are obtained for free from crossing. And this expression here is actually only valid when n is greater than 1. And the case of n equals 1 is a bit special because here you do not get enhanced logs, right? Because n equals 1, you can get at most log v, and the conformal blocks, they already have log v, so it can be prooted by finitely many conformal blocks. So this n equals 1 case actually needs to be fixed by hand. Okay. Now the final step is to just map this logarithmic correction to the 4-point function to logarithmic correction of the EEC using this map I showed you earlier. And doing so, you find this expression at n loop. And because n here is arbitrary, you can actually resum it to all orders in coupling, and you get the following result. And this the ERF function here is an error function. And we check the explicitity of this back-to-back limit result with the back-to-back limit of the 4 EEC calculation, which has been known up to 3 loops. But the result for n greater than 3 is new. Okay, so that's the main result of our calculation. Now let me try to conclude and maybe mention a bit of future directions. So in this talk, so basically I just described how to use very standard techniques from the analytic conformal bootstrap to compute subleading corrections of the energy correlator in the back-to-back limit. I think there are many interesting things which can be done in the future. So, so here the back-to-back limit is related to the double light cone limit of the 4-point function. But there are also other interesting limits of the 4-point correlator. An interesting limit is the ridge limit. So it might be interesting to understand how this ridge limit is mapped to the EEC, and to know what kind of non-trivial constraints does the 4-point function ridge limit impose on the energy correlator. Another thing to be noticed here is that we only made a very preliminary use of the analytic conformal bootstrap. And I think one can push this further. Let me here maybe just mention a fact which well, it did not play a very big role for us in this talk, but so the fact is that in this EEC, because you have a time-like momentum from the Fourier transformation of these two J's, you are actually breaking the conformal symmetry, and the conformal symmetry breaking is actually the same as putting a conformal field theory on a real projective space. So this is kind of obvious if you go to embedding space, where there's a C2 quotient that makes RD into RPD, is also just to have a fixed time-like vector. So as a result, the so-called celestial conformal blocks for the EEC. So yeah, so the 2-point, so the EEC, you can also decompose that into some basic building blocks fixed by conformal symmetry. These are called the celestial conformal blocks. And they actually turned out to be exactly the same as the 2-point functional conformal blocks of CFT on RPD. And in a paper I wrote with Simone Giombi and Himanshu Kanchandani, we developed some analytic functional method to extract constraints from the crossing equation of 2-point functions. So it'd be interesting to see if this technology will be useful in studying the energy correlator as well. Another kind of bootstrap application is to imitate the game people usually play in amplitudes and correlators. So what people usually do is just to guess the basis functions for the object you want to compute, and then you use consistent conditions or and some CFD data, try to fix these coefficients. And the same game can also be potentially played here. And finally, it would be interesting to see if one can make a connection with the numerical bootstrap. Although the issue here is that positivity is a bit unclear. So right, so like this collinear limit is related to an OP limit of the 4-point function, and therefore it has some sort of positivity. However, this back-to-back limit is not really an OPE because these operators are never close to each other. But maybe like there's also another limit where you do kind of an OPE between the source and the detector. So yeah, but anyways, it might be interesting if one can make this positivity a bit more, yeah. Or alternatively, one can also try to maybe do some kind of bootstrap of along the line of this clearly truncation method. but anyway, so yeah, let me just stop here and thank you very much for your attention.
All right, thank you. Let's thank you, guys. Any questions?
So in principle, positivity, if you iterate over the position of all the angles of your colorimeters.
Mhm.
So that's a constraint, right? That you in principle use.
Yeah, it's also right. The EEC is also, it has to be positive for all angles, yeah, because it measures the energy, yeah.
By the way, what is known about 3 colorimeters?
There's a paper by DSD and his students, I think maybe last year.
But does it relate it with a 5-point function, or does it compute it? Okay.
Precisely, yeah, iterated the 5-point function, yes.
Okay.
Yeah, but I mean, I think like in the case of angles polynomials, because everything just comes from the 4-point function of 2D prime, so I think the positivity of 2D, I mean, the 4-point function should be inherited somehow, right, by the EEC.
Yeah.
So it'll be interesting to see if this can be made more precise.
And is it interesting experimentally to measure 3 energy correlators?
Sorry, what about 3 energy correlators?
Yeah, it is very interesting to check against experiments, or if there are experiments that are sensible to that.
Right. Yeah, I don't know much about the experiments, but I imagine it will be very interesting to look at the case where you have more detectors.
But those would be sensitive to 3-jet kind of interactions, right?
Not necessarily, right? Like you can just put like all 3 detectors in the same jet. So it gives you more information than, you know, probing that with just 2 detectors.
Mm-hmm.
One question.
Are there implications to type 2B? Does that work?
So the question was, are there any applications from this work to type 2B string theory?
Yeah, so right, so I guess you're asking about strong coupling. So in strong coupling, the result is a bit boring. So there are no jets at strong coupling. So basically the EEC is just a flat line, like yeah, like all the directions are the same.
Thanks. Any more questions, guys? I guess not. So if there are no more questions, let's thank Xinan once again.